In section 8.1, we're going to be looking for graphical solutions to trigonometric equations. So first of all, we're going to solve these by graphing. At the same time, we'll be thinking about some of them algebraically and just what we know from the previous chapter. We'll also be talking about the solutions, the complete solutions, which means that oftentimes the solution is not a single answer but an equation. And just a little bit of background, the basic trigonometric equation is going to be an equation that's set equal to a number, and oftentimes it's one trigonometric equation equal to another trig equation. So the first example I hear, we're asked to solve the tangent of x is equal to -1. Now, if you're thinking about the tangent of x and when it's equal to -1 and you think back about the graph, then you know pretty quickly that you know the answer to this, and that would be -1 there at -pi/4. So you already know that the answers are going to be that x is equal to -pi/4 plus pi times k, where k is an integer, any integer. So let's talk a minute about that. First of all, we have pi, and why do we have pi? We have pi there because the period of this function tangent is pi. And so we would have, if we were to look at how this were to continue, which would be easier if we were to look at a graph, then you would see how that solution would continue for infinitely many options here. So looking here on GeoGebra, I have the graph of tangent, and I'm just going to modify this a little bit so that we can see the graph of tangent. And then I also have the graph of the line y is equal to -1. Okay. And if we go and we find one solution to that, so that would be finding the intersection, then we can see that that intersection happens, and you can tell here that intersection happens at -0.79, -1, which is approximately -pi/4 there. We also get other solutions, and those other solutions happen here and here, and it continues to happen in increments of pi. And so that's why in this case we give solutions as not just as the -pi/4, but the -pi/4 plus the pi k. Alright, and now for the next example, this one we're solving the sine of x is equal to 0.33. So there's a couple of different ways to do this. First, you can put this equation in as y1 and put this in as y2, and then find out where the two intersect. So here's your sine function, and what's going to happen is that you have your x-axis here, and so 0.33 is going to be somewhere up here, and what we're doing is we're looking for the intersection of those two, where y1 and y2 intersect. And so you can see that we would be expecting two solutions here. Okay, so let's look for a graph there. And I've already entered these equations in, so here I have sine of x, and you can see one period of sine of x, the period is 2 pi, and then let's see y is equal to 0.33, and that would be this line right here. And so just as expected, we see two solutions there, and let's find those intersections. You can find these intersections on your calculator. So to find those intersections, I'm going to come over here, find the intersection of the red line and the black line. And you see the first one happens, it tells us where x is at about 0.34. And then let's find the second one, would be here at 2.81, and what's going to happen here is that is going to continue. So if I'm considering that period, let's capture a picture of that. that didn't work out so well. So what's going to happen is as this continues here, then we're going to continue to have solutions, one here and one here. And what we need to realize is that from here to here, as far as the distance on x is going to be 2 pi, and from here to the next one is 2 pi. And so that continues in increments of 2 pi, but again, because of our period being 2 pi. So what we've done is we identified this right here as x is equal to, it was about 0.34. Okay, and then we've had another one, and that would be the second one here, at about 2.81. So those are the two solutions within the interval from 0 to 2 pi. And now if we're finding all solutions, then what we're going to do is say plus 2 pi k, where k is any integer again. Okay. And here we have an example that's a little more complicated. In this case, what we would want to do is put this in as y1, put this in as y2, and find out again where they intersect. The tricky part is putting this here into your calculator. When you put this into your Texas Instruments calculator, you're going to need to put it in like this. You notice it's the cosine squared. So you would put in cosine of x like this, and then square it. And then the rest of it you enter as you usually would. Okay. So we're finding the solutions. We want to know when this is equal to 0. So the tricky part to begin with is going to be to find out what the period of that function is. So here's the original function, and you can tell that we don't exactly have a great graph, and there's also some things going on that are a little more complicated. So I'm going to zoom out on this a little bit, and now you can sort of see what's happening here. You've got your period moving. If you were to go from this point right here on your y-intercept, then it would start to repeat as you got to this point here. And so that means that your interval, you could say that your interval was 2 pi. So even though it looks complicated, it's actually not that bad. And hopefully you also notice that each of the cycles has in it one or two relative minimums. Okay. And so now what we need to do is find out when that is equal to 0. So we also have the graph of y equals 0 here, and that's just on our y-axis. So if we're looking on the period from 0 to 2 pi, we've identified that 2 pi is our period. So we want to find out, in how many cases do we have some intersections. So the first one, it looks like, would occur right here. And so if we find that intersection, it looks like that one is at 1. And I think I actually have an equation in wrong here. Let's see, this should change. Oh, actually, no, this is fine. This is fine. This is right. Okay, so the first one here is at approximately 1. And then we have another one here at approximately 2.14. And then we have a third one just after pi. We find that intersection. And it looks like that one's at about 3.78. And then, and note we are looking at the x-coordinates because the y-coordinates are actually 0 in all of these cases. And then we have one more, and that one is going to occur at about 5.65. Okay, so we have within the interval of from 0 to 2 pi, we have exactly 4 solutions to this equation. And so now, the way we would write those would be, first of all, we had one at approximately 1. We had a second one at approximately 2.14. The next was at about 3.78. And then the last one was at about 5.65. Okay? And so for each of those, we want to add 2 pi k to give the complete solution set. So again, this means that there are infinitely many solutions. And we know again that k is any integer. Okay? And so going back to look at that again, if we were to move the view of this graph, we could see that there are infinitely many solutions, because this function, this blue function, will continue to intersect this horizontal black line here in infinitely many locations. Okay, so just a summary of what we've been doing with these equations is, first of all, we've written the equation in the form of f of x is equal to 0, and actually we did not do that in all. So if you go back and you think about the second example I did, sine of x is equal to 0.33. I chose not to write that one in the form f of x equals 0. I actually entered that as y1 and that in as y2. And then I found the intersection. So this is optional. You could also take this method. Then we determine the period of p and of f. So what we did is we determined the period by looking at the graph. So if you look at the graph, you can see the key is what you're looking for is how long before you see repetition. And when you determine that, then you can determine your period. And so then the next thing you would do is graph over at least that period p. More is fine, less is not okay. And then we'll use the calculator's zero finder. So that would be your second calc and find the 0. Or you could second calc and find the intersection. Intersection is also an option here. If you choose this method, you would be looking for the intersection of y1 and y2. And then you write the solution as whatever your solution is on that interval plus k times p, where k is any integer and p is your period. And those would be your solutions. Okay, so let's try a couple more examples. This one we have tangent of x is equal to -4 cosine of 2x. And so this one, the way I'm going to enter it again, this is what I prefer. Enter this as y1 and enter this as y2, and you can do this on your calculator and find out where they intersect. If you think ahead to what you know right now, you know that the period of tangent, in this case, is going to be pi, because the value of a is 1. And here in this case, you know that the period of your cosine is going to be 2 pi divided by that a, which is equal to pi. So it's likely that the period is going to be pi here. So let's take a look. And let me get the correct graphs up. I've got tangent of x, so it's our red function. And then the next one is -4 cosine of 2x. And you can see this is confusing here, so I'm going to zoom into my x-axis and see if I can get a clear picture of what's going on. And here it starts to get better, And remember, we assumed that our period would be pi, and it looks like that's exactly what's happening here, is that our period's pi, because we notice one intersection here and a very similar intersection right here. And then we also notice an intersection here between 1 and 2, and then another intersection over here between 1 and 2 that are similar. And it looks like that pattern would continue, okay? And so now the task is to actually find those two solutions. So finding the intersection, let's go for the first one, the intersection of the function p and q. And it looks like that intersection is at about negative 0.68. And you can see that here. It's labeled point E. And then let's find the second one. Again, the intersection, point F, and it looks like that one's at about 0.97. Okay. And, you know, this one, if you stop here, you might think you're done, but if we look up a little bit further, actually, it looks like I missed one. So make sure, the lesson there is to make sure you're seeing a complete graph, and we weren't seeing a complete graph of, especially we were not seeing a complete graph of our cosine function because we were not able to see its peak. So we are going to go through and find one more intersection. And that would be here. And it looks like that one is at about 1.28. Okay, so within that period, we have 3 solutions, and so we would note 3 solutions, 3 equations for solutions. Okay. So the first one we mentioned was negative 0.68. The next one was 0.97. And then the third one was at about 1.28. Okay. For each of those, we have decided that the period here is pi. So instead of adding 2 pi k, this time we'll actually be adding pi k. So plus pi k, plus pi k, plus pi k. And this again would give us all the solutions, and again we need to note that k is any integer. Okay, and one last equation. This one, again, you've got a cosine squared, so be careful about how you enter this one into your calculator. Do it as we did last time. What I would do is probably enter this one in as y1 and this in as y2 and find the intersections again. Or if you're using your calculator, you can, as long as the y2 is equal to 0, you can just find the zeros and you would do left boundaries and right boundaries. Either of those methods would be fine. There we go. Okay, so here we go for our last ones. And you notice this function is a little bit different than some of the ones we've seen. I'm going to take off some of the points that we have here so that it's not quite so confusing. Okay. All right. So we can see the function r of x, and that's the graph of this 3 cosine squared x minus 2 cosine x minus 3. And here it's a little bit hard to see what the period might be. So if I zoom in a little bit, we start seeing some repetition there. And it looks like we can go from the peak down here at negative 3 to this peak right here, and that would take care of everything. So each cycle is going to have 2 local maximums, and it's also going to have 2 local minimums. Okay, so here's your local minimums. Your local maximums would be here at negative 2 and at positive 2. Okay, So we're ready to find our zeros, or we're ready to find the intersection at this point. And see, it looks like the first one might be here. Okay, and so here we notice that we have one at about 2.38, and then we have another one here at about 3.91. Okay, and that's it for the cycle. So using those two solutions, we can write our complete solution set. And 2.38 and 3.91, plus we notice that we had a period of 2 pi, so 2 pi k, and k is any integer again. And that's all I have for section 8.1.